Okay, so this next problem I'm doing is from Chapter 1, Problem 12 in Classical Mechanics. And the problem states that the escape velocity of a particle on Earth is the minimum velocity required at Earth's surface in order that the particle can escape from Earth's gravitational field. Neglecting the resistance of the atmosphere, the system is conservative. From the conservation theorem for potential plus kinetic energy show that the escape velocity for Earth, ignoring the presence of the moon, is 11.2 kilometers per second. Okay, we really don't have to write any of that down. We just have to know that the conservation theorem is just saying that you have the total energy, so you have K1 plus U1. So you have this like basically our total energy here is going to be equal to our final energy. And so essentially, if you are in this problem, probably the hardest part about this problem is just visualizing it. So if you're on the Earth and you're trying to escape the Earth, you want the minimum velocity. You want the minimum velocity to escape. And so that's going to mean that you've escaped, but then you stopped, right? And that's going to happen at what we refer to as infinity. So with our potential, especially gravitational potential, it's defined as coming from infinity to the center of the radius, so whatever that is, right? So at this point, we should know that your kinetic energy is 1/2 mv squared, right? P squared over 2m, same thing. Let's get rid of these little suggestions. I don't like those. Okay, so, and then your gravitational potential energy is negative the gravitational constant times the mass of the Earth with the mass of the thing escaping, so U, right? And then under that is going to be the radius of the Earth, okay? So that's it. But what about K2 and U2? These two, so when you are at infinity, okay? Put it in quotation marks. When you're at infinity, your U2 is 0, because that's where you're starting from. So that's 0. So your K2 is also going to be 0, because it's your minimum velocity required, okay? So this is the trickiest part about the whole thing, is just knowing that these two have to be 0. So if that's 0, that means that your K1 is equal to positive U, right? Or negative U, which is this positive. See that? So we can just write this at 1/2 mv squared equals, so it's pretty straightforward, GMM over R. And then you can see we have these two m's that cancel out because it doesn't depend on your mass. That makes sense. You can carry the 2 over, do some algebra, and you get V equals the square root of 2 GM over R. Now we're just, at this point, we're done, right? We just got to plug in our numbers. So G equals 6.67 times 10 to the minus 11 Newton meter squared over kilogram squared. Now, let's just write this out. So newtons, remember, are kilogram meters per second squared, okay? And then we have our m, mass of the Earth, which is, if the internet is not lying to me, it's 5.972 times 10 to the 24 kilograms. It should be good enough for our homework problem. And then R is 6,378,137 meters. Okay, so to make sure that you did everything right, what I like to do is always just look at the units, right? So you have kilogram meters over second squared, right, times meters squared over kilogram squared, okay? That's G. Then we have M, which is, you have a kilogram up here, right? Now we go, our R is meters. So there's a whole bunch, but at the end we should have meters per second. So, and then this is, so one of our meters goes away. our kilograms all go away. What are we left with? We have 2 meters, so we're left with meter squared over second squared. The square root of that is meters per second, and that is exactly what we need, so you know that you did it correctly. So you should always check your units and make sure that it came out correct. So when you do this calculation, it comes out to 11.176 kilometers per second, or 11.2 kilometers per second. So we're done.